yesterday we looked at, or the earlier video, we looked at what it means to be a vector and how to add vectors. So today we're going to just recap quickly multiplying by a scalar and what this does geometrically to a vector, but we're also going to look at what is equal vectors and what are parallel vectors. So we know what a vector is, and we know when we multiply a vector by a scalar, or we multiply a vector by a constant, we just take that constant inside the vector and multiply each component of that vector by the constant. Here are our examples. If our vector A equals 1 minus 3 in column vector form, compute and sketch minus vector A, a half of vector A, and 2 times vector A. So if we have minus A, we just do minus 1 times 1 minus 3. So minus 1 times 1, that's just minus 1, and minus 1 times minus 3 is a positive 3. If we have a half vector A, again times each component of A by a half, and we will get a half as our first component and minus 3 over 2 as our second component. Lastly, if we have 2 times vector A, again multiply each component, we will get 2 negative 6. The second part of the question was to sketch this. So I've just put the vector A in, which is 1 across and 3 units down. Negative A, I'll do this in a different color, is minus 1, 3. So you go left 1 unit and up 3 units from the origin. Notice here, when you have minus 1 times a vector, say vector A, this does something geometrically to the vector. This rotates vector A 180 degrees about the origin. Or you could think of it, it takes vector A and flips it in the origin opposite direction, but the length of that vector is the same. If you multiply a vector by negative 1. If we multiply a vector by a half, this vector, if I go a half right and minus 3 over 2 or 1.5 down, I actually end up in the same direction as my original vector, but the length is halved. And I think you know what's going to happen for the last one. 2a, I'll have the vector 2 minus 6, so go 2 to the right and 6 downwards. This is going to be the same direction as a as well, except now we're going to see the length of this vector will have doubled. So that means a few things happen when you multiply a vector by a scalar. Also multiply a vector by, say, minus 2 or minus 3 or minus 4. So that will make it in the opposite direction, but the length of the vector would be either tripled, quadrupled, etc. We're going to compute a simple multiplication, 6 times the vector 2, 9, okay, and this will just be 12 and 6 times 9, 54. Lastly, I want to find the value of x, where x is a scalar and a real number in the following vector equation. I have x times the vector 3 minus 4 plus the vector 1, 2 equals the column vector minus 5, 10. I start like solving a usual equation. First, let's do the multiplication. We'll get x times 3 and x times minus 4. I still have the other two vectors here. Our next step is to add the vectors on the left-hand side. And remember to do this component-wise and we'll form a new vector here. 3x plus 1 and minus 4x plus 2. This will still equal minus 5 and 10. Then you separate these into two equations. The first component all the way across, 3x plus 1 equals minus 5, and the same with the second component, minus 4x plus 2 equals 10. What we do now is we solve each equation for x like we normally could do, and hopefully we'll get x is the same number. If x is not the same number in both of these equations, this whole system of vectors cannot be solved for x, it would have no solution. But luckily when I solve both of these equations, I end up with x is negative 2. That tells me the solution for x is indeed negative 2. So we know that multiplication by a scalar simply shrinks or stretches a vector. If the scalar is negative, then it will also make the vector appear in the opposite direction. If one vector can be written as the scalar multiple of another vector, these vectors are parallel. So notice in this diagram, I have u, 2u, a half u, and minus 1u. These three bottom vectors are all scalar multiples, or just a constant time vector u. Even though some are in opposite directions, they are all parallel to each other. So these vectors are called parallel vectors. Vectors with the same magnitude or length and the same direction are equal vectors. Okay, equal vectors do not have to start in the same location. They just need to have the same length and be in the same general direction. So any two vectors that are parallel and have the same length are equal. So these two vectors that I've just drawn, although they don't start in the same spot, if they have the same length and they're in the same direction, they are called equal vectors. Let's try some examples. Is the vector 3, 9 parallel to minus 21, minus 63? The only way 3, 9 would be parallel to this vector is if I could times 3, 9 by a scalar, and that would equal minus 21, minus 63. So all we do is we solve this equation for our scalar in this case. So we have 3 times gamma and 9 times gamma equal minus 21 minus 63. Again, equate the first components and then the second component. So can you solve 3 gamma equals minus 21 and 9 gamma equals minus 63, where the solution for gamma is the same? If we do minus 21 divided by 3 to solve for gamma, we get minus 7. The same with minus 63 over 9, we'll get minus 7. Therefore, we can say 3, 9 is parallel to the vector minus 21 minus 63 because minus 7 times 3, 9 is equal to minus 21 minus 63. For the second part, we've got to check if 3, 9 is parallel to the vector minus 14 minus 19. So we do the same thing. Again, we have our variable or our constant times it by 3, 9. And we see if there is such a constant that this is true. So first equation, 3 gamma equals minus 14. Second equation, 9 gamma equals minus 19. Divide the first equation by 3, and we'll get gamma equals minus 14 over 3. For the second equation, we'll get gamma equals minus 19 over 9. Notice that these gammas are not the same. Minus 14 over 3 is 4 point something. Minus 19 over 9 is, I think, 2 point something. Okay, these are not the same. So therefore 3, 9 cannot possibly be parallel to the vector minus 14 minus 19. And if you sketch the vectors 3, 9 and minus 14, minus 19, you will notice that they are not in the opposite direction of each other and they are not in the same direction of each other. Therefore, they're not parallel. Lastly, in the diagram below, we're going to identify the vectors that are parallel and the vectors that are equal and the vectors that are negative multiples of each other. Let's find the parallel vectors. So remember, same or opposite direction, and they can be of different lengths to each other. Let's assume that this hexagon is an hexagon where all the lengths are the same. So it's a regular hexagon. I can see 3 pairs of vectors that are parallel. ED is in the same direction as AB. EF is in the opposite direction of BC, so they are also parallel. And there's one more. FA is in the opposite direction of DC. They are also parallel vectors. B, remember they're equal if they're parallel in the same direction only and the same length. The only pair of parallel vectors that are in the same direction and the same length here are ED and AB. So they are the only 2 vectors in this picture that are equal. But they would only be the same length if this hexagon was regular. Part C, which vectors are negative multiples of each other? So we know they're negative multiples of each other if they're in the opposite direction to each other. So that means EF and BC would be negative multiples of each other. And we also know that FA is parallel but in the opposite direction to CD, and FA is the same length as CD, so FA could be described as negative CD. Guys, that's the end of our first lesson on 20A. I hope you enjoy the beginning of vectors, and I hope you like this little dinosaur as well. It only speaks the truth.